The atom is the basic unit of matter that consists of a dense, central, positively charged nucleus surrounded by a cloud of negatively charged electrons. The Rutherford gold foil experiment was first suggested by Ernest Rutherford and conducted in 1911 by Hans Geiger and Ernest Marsden. The experiment involved shooting alpha particles at a gold foil to observe how they were scattered by the gold on a screen. This process probed the structure of the atom, because if it were a solid mass, few if any alpha particles would get through. If, as they expected, the atom consisted of negative electrons that were embedded in a thin positive mass, all of the alpha particles would get through. However, what they found was that most of the alpha particles get through, with some of them being scattered by the small positive nucleus. The conclusion was that the atom is mostly empty space, consisting of a small positive nucleus surrounded by electrons scattered throughout the surrounding space. The difficulty is that in such a model, the electrons cannot stand still, because if they did, they would fall into the nucleus. This led to modeling the atom as a solar system, with electrons orbiting the nucleus like planets around a star. The problem with the planetary model is that electrons are charged particles, and an accelerating charge emits light, losing energy. This would cause the electron to spiral into the nucleus. The Bohr atomic model was based on the fact that Broglie had shown earlier that particles such as electrons have wave-like properties. Bohr then showed that these waves could be bent into orbit, like those expected for an electron. Bohr further showed that electrons can only occupy those orbits with exactly a whole number of wavelengths. In these orbits, the waves are added together with constructive interference. A fractional number of wavelengths would destructively interfere and not persist, so an electron cannot occupy such an orbit. The result is that electrons jump from orbit to orbit, with photons emitted when going to a lower orbit and photons being absorbed when going to a higher orbit. It turns out that the transitions between the possible electron orbits match the spectral lines actually observed in hydrogen. This was a major step in the development of quantum mechanics. Further developments have come from studying elements other than hydrogen, including the effect of multiple electrons. These studies resulted in the electron orbitals shown here. They are the places in an atom where electrons can actually be found. The shapes of these orbitals were originally found mathematically. They have long been viewed as purely mathematical abstractions. The orbitals were never expected to be seen. Physics students have long been told this. However, field emission electron microscopy has changed this. Here is a mathematically generated s orbital image. Here is a field emission electron microscopy s orbital image. Here is a mathematically generated p orbital image. Here is a field emission electron microscopy p orbital image. The imaging of actual electron orbitals was a surprise. However, it vividly shows the accuracy of quantum mechanics.